We see the future of computing as being the combination of bits, neurons, and qubits, right? So from the point of traditional computers, AI-based compute, and quantum compute, right? And in fact, we're already seeing a lot of this integration.
Is the age of quantum supremacy almost within our grasp? Hello and welcome to Tech First. My name is John here. We've seen some insane advances in quantum computing recently. Microsoft says it has a path to large, capable quantum computing with its Majorana chip. Now, IBM says it has a clear path to a massive quantum computer that can run 20,000 times more operations than today's machines, quantum machines, and would be vastly more powerful than even our classical supercomputers. This is IBM Quantum Starling. IBM says that representing the state of Starling would require the memory of more than a quintillion of the world's most powerful supercomputers. Wow. Here to chat is Jerry Chow. He's an IBM fellow and director of quantum systems. Welcome, Jerry.
Good to be here.
Super good to be here. And let's start here. Where is here? What's behind you there?
I'm sitting in Yorktown Heights, New York, in the IBM TJ Watson Research Center, and behind me is actually IBM Quantum System 2, the first that we've ever installed, and it's right here in the Think Lab as a representative of the future of computing. So actually all around me, there's a mainframe system over there. There's an AI supercomputer, a GPU-based computer over there, and then we have our quantum computer, which holds 3 of our most advanced Heron processors sitting right there.
Impressive. Okay, second question. What the heck is a quintillion?
It's a very, very large exponential number, right?
And you knew that already.
Yeah.
Give me some more
10 to the
detail.
48, 10 to the 48, right? So it's a ridiculous number and meant to more just show that really, as you scale the number of qubits, that the state space to represent that state is just immeasurable, right, from a classical point of view.
It's literally off the charts, I'm going to say that quote again. Representing the state of Starling, this is from the IBM press release, would require the memory of more than a quintillion of the world's most powerful supercomputers. These are supercomputers with thousands, tens of thousands, in some cases, hundreds of thousands of processors all linked together. Clearly, there's zero chance of us ever having a quintillion of these things on planet Earth, at least. But impressive. Right. What's the announcement today? What are you announcing?
So we're really announcing that we have a very well-defined architecture and roadmap for really reaching that target of a fully fault-tolerant quantum computer by 2029. And there's a lot of discussions in the news about ideas of error correction and thoughts of how to demonstrate some simple experiments. But we really want to show that we have a path which is technologically focused, year after year measurable in terms of targets to hit, that really gets us to that point in 2029 where we'll have a 200 logical qubit machine with Starling.
It's crazy, hey, because we have functioning quantum computers today. There's some behind you right now. There's a number in the market. There's some that you can buy, some that you can access in the cloud, other things like that. And they're doing some things today that you can't do with classical computers, but we haven't literally changed the world yet. We haven't literally absolutely classical computing can't even begin to compete in certain areas. This roadmap that you're talking about is pretty mind-blowing in that sense. What's the key technological advancement that enables this?
Yeah. So in a lot of the literature, right, and in a lot of the discussions about how to build quantum computing fault-tolerant processors, it's been focused on something called the surface code, which is a error correction code for building towards fault tolerance, which actually relies on a nearest neighbor lattice of qubits. So it's a square grid array. But the problem with the surface code is it's a very well-studied code, is that it requires a large overhead of physical qubits. And so when people have been talking about building machines of that scale, it requires some on the order of millions, if not tens of millions of qubits.
Ouch.
Right? So something which certainly we didn't want to go and just find a way to go build at that particular level, right? And so we actually relied on working very much hand in hand with our theory development team, right? So our error correction development team to come up with a new novel code. So a much lower resource code, and it's called the bicycle bivariate code. We actually published this paper a year ago in Nature showing that it had the potential for a 14x reduction in the overhead from the service code. But then right now, what we're really showing is also on top of that, there are other pieces of the puzzle that needed to happen to make it a really tenable architecture in terms of running logical operations, in terms of having a real-time decoding technique. And we just published results on that. We posted it to the archive, really, and showing that we really have a path to make this viable in this time scale towards 2029.
So this is crazy, right? If you have to have millions of physical qubits to make one logical qubit because you need them for error correction, you can't just pick up physical qubits at the supermarket. These are not easy.
That's right. And with any physical qubit architecture, you need a way to actually build them and scale them in a way that you're doing so, well, on one side, making them high enough quality, right, to actually support any kind of error correction codes. But on the second side is also, how do you do it in a cost-effective way, right? You need to build infrastructure around it. And you need to have the right methodology of system integration.
Yeah.
And so we have system integration has been part of our DNA, right, in terms of building these quantum computers from even when we first started putting these out in the cloud. That's why we have Quantum System 2 back here. We have actually behind it over there is Quantum System 1, right? We've been thinking a lot about how to systematize it, right? And we have now an architecture, core Starling also, that is manageable, right, in terms of scaling. And also just with further improvements and refinements to a lot of the rest of the ecosystem, we're just going to continue to make that more and more, so it'll be more and more compact, and it'll be more and more economic.
Wonderful. I have a quantum computer going here. Apparently I've got one of my lights just going nuts here. So I'm just going to totally turn those off. This is real life. I don't actually have a quantum computer here. There are probably quantum operations happening behind me. We'll see. So how confident are you in this roadmap? Like you've got some technology.
Yeah.
You've got the path, you have the theory. It actually has to be done now. How confident are you?
Yeah, so a big part of executing this roadmap really comes down to the technological development that we have at IBM. Roadmap is also in our culture. We've been hitting our targets year after year in terms of showing new technologies that allow us to scale. It's how we hit 100 qubits back a few years ago. It's how we hit the 1,000 qubit barrier with Condor a few years ago. But this technological innovation really comes down to how many cycles of learning can I get to build these types of devices over and over and learn new things. And with the bicycle bivariate code, it actually requires a much more intricate connectivity than the service code, right? So it's not just a square lattice. It actually requires a much more highly connected lattice, which requires more layers of your quantum processor all connected together. And we've been developing advanced packaging techniques by leveraging IBM's deep history in semiconductor fabrication and development to teach us ways of doing this advanced packaging at scale, but even with our superconducting qubit devices. And so that's why we have a lot of confidence in being able to build this. We have a very unique processor architecture, right? And so we're going to see a lot of those pieces come together in a device by the end of this year, Loon, that really starts to lay out a lot of these various pieces. And then we're going to scale out further towards the other parts of the roadmap in the years to come.
I'm sensing a theme here. Loon is a bird. Blue Jay is a bird. Starling is a bird.
We got it. They've all, the heron is a bird. Yeah. First one that ever came out was a canary, right? So
excellent. I'm waiting for the eagle.
We've had eagle.
Ooh.
Eagle was our first 100 qubit machine, and that we released several years ago, right?
Excellent. Yeah. Talk a little bit about these quantum processors. Like, what does it take you to build a qubit and integrate it into this multi-level lattice? How difficult an engineering problem, a manufacturing problem is it?
Yeah. So the qubit devices that we build at IBM they're superconducting qubits, and they require basically a superconducting element called a Josephson junction. Okay. And it consists of having a simple sandwich of superconductor, insulator, superconductor. Okay. And
I love
then,
it when quantum physicists talk about simple. Yes,
but the whole point is that we're building physical circuits with circuit elements. Think about capacitors, think about inductors, and then you're adding in this extra superconducting circuit element called a Josephson junction. So you take all those pieces, you throw them into a circuit design toolbox, right? And you end up building up these networks of interconnected circuit elements that can behave quantum mechanically in different parts as qubits and are connected together so that you can perform operations like entanglement operations, so they can control them to perform single qubit gate operations, so that you can read out this qubits, so that you can determine whether the state was in a 0 or a 1. But really then it comes down to how you lay it out, right? How you actually connect these various qubits. With devices like Eagle and with Heron, our layouts have been relatively simple. They're in a planar geometry. We can make these gate connections between various qubits you can draw it on a piece of paper.
Yeah.
With Loon, and we have a visual that can actually show like how interconnected it is. You're really connecting each qubit to 6 other neighbors. Some of them might be next to you, some of them might be far away. And so you have to do that by using other layers. So things that are happening in your integrated circuits of your laptop and your phone, right?
Yeah.
That's very common to have multi-layer type of wiring. But we figured out how to integrate that even at the scale of these superconducting qubits to preserve its quality and allow us to have that very highly connected lattice.
You're going 3-dimensional from 2D.
Exactly. You got it. That's a big part of the innovations.
Building these qubits and simply drawing them together, is that a bespoke process, or is it ever something that will lend itself to mass manufacturing?
I would say that. So going through this, I've been working with superconducting qubits since 2005, and it's always been a rather bespoke process of design, and you simulate, you design, and you lay out by hand and simulate. But then over time, we've really developed a lot of the toolboxes that you need for advanced manufacturing methods, advanced simulation methods to really get parameters close to first time right. Because you don't want to have to iterate, make various different types of designs, and then be surprised when you actually make it. Because as we make these devices more and more complex with these many layers, you can't really afford to make those types of mistakes, and you need to keep those cycles of learning up. And so we are starting to use a lot of these sort of advanced techniques of layout and so forth.
Cool.
Yeah.
Let's talk a little bit more
visual here, if you want.
Yeah, absolutely.
So this is what the layout of Heron looks like, right?
Yes.
And then here's what the layout of Loon is in a cartoonified form, right? But that's the connectivity that we're talking about. When you need to have 6-way couplers across many layers connecting all these various qubits.
It almost makes me think of like a physical neural network, neurons multi-connected to physical neurons and biological neurons almost is what it reminds me of. Kind of crazy.
Yeah.
Let's talk about Starling and Blue Jay. A couple quotes from the press release. Starling will be able to access the computational power required for these problems by executing 100 million quantum operations using 200 logical qubits. So 200 logical qubits, 100 million quantum operations. Over what period of time is that? Per second? What is that? So
you can think about this. That's where we will have accurate circuit runs of that size, right? Okay. And so the timing will end up depending on various elements of how we end up building the error correction decoding algorithm and everything like that. And so the full circuit time is still something that we're working on, right? But you need to also think about that. That's not solving one problem yet. any kind of problem you solve requires running multiple quantum circuits. This is what people do today already, even with our Heron devices. You're running many, many quantum circuits, sometimes thousands, if not hundreds of thousands circuits, but in concert with classical computing. So what's actually more important is how quickly are you getting that information from your quantum computer into your classical computer, crunching it there together for your full solution to a problem.
Absolutely. And getting that interconnection really tight, making that work, a challenging problem. Blue Jay, built to run 1 billion quantum operations over 2,000 logical qubits.
Yep. So that's to another degree, right? For 2033, 2,000 logical qubits scaling up to that size. So the way to think about these numbers of qubits and numbers of gate counts. So there's a lot of research out there that's been looking at what are the resources required to solve some of these very hard problems that we know that there's probably quantum advantages in, like in looking at chemistry types of problems. Some people, of course, all very interested in the factoring algorithm, right, for breaking encryption. So most of these resource counts, though, all put it in the realm of needing several billions of gates and hundreds of thousands of logical qubits.
Mm-hmm.
But a big part of also where we're going with our roadmap, which is a continuous path from where we are today with Heron and soon Nighthawk, to that Starling and Blue Jay scale, is to use the machines to actually find more efficient algorithms, right, along the way, and push a lot of those resource counts down.
Yes.
So we're already in the realm today with our machines where you've mentioned it yourself, that you can run quantum circuits which can't be simulated classically.
Mm-hmm.
But what is it useful for? Well, that's part of a lot of the algorithmic discovery that's absolutely critical in this coming phase, because people are going to see, well, what can I run on hundreds of qubits and thousands of gates today?
Mm-hmm.
And then they're going to work out, okay, well, when I get to millions of gates or hundreds of millions of gates, I'm going to run that type of problem, right? And so there's this almost empirical exploration of new algorithms, right, that's going to emerge and drive applications that is so exciting, right? And part of also why this is not we're not making this announcement and just saying, yeah, wait for us in 2029. It's coming in 2029. Get started with us today already with the machines that we have,
Mm-hmm.
and work your own path with us towards 2029.
It blows the mind because we've already seen some amazing things in drug or new chemical compositions with AI and existing supercomputers and clusters and everything like that. And when we have this kind of quantum power to approach problems from an entirely new way and approach an entirely larger set of potential solutions and see which ones work best, it's going to be mind-blowing. Contextualize it a little bit for us. What does this mean and what changes when this becomes reality?
Yeah, absolutely. Like, I think you hit on a really important point in terms of how quantum is really going to intersect with high performance computing and supercomputers today, right? That's part of our vision of what we call quantum centric supercomputing, right? That we see the future of computing as being the combination of bits, neurons, and qubits, right? So from the point of traditional computers, AI-based compute, and quantum compute, right? And in fact, we're already seeing a lot of this integration. So we've been working with collaborators out in Japan with the Fugaku supercomputer out in the Riken Institute there. And we've actually been working on an algorithm which looks at ground state energies of complex molecules that do one part of the calculation on our quantum computer, passes it off to that supercomputer, and then they perform a classical diagonalization on that supercomputer using a lot of those resources. And we've been finding that we can actually get accurate results for molecular structure of iron sulfide clusters. So pretty complex, large molecules that are also competitive with the best supercompute-only methods. So we're not beating them yet in terms of accuracy, but we're on the same playing field with the most advanced classical-only methods. And as we iterate and we find the right balance of using quantum and and classical supercompute, we expect to cross that, right? We expect to be more accurate than a supercompute classical system alone, and that'll really be a quantum advantage.
Cool. And was that in pursuit of novel or new battery technologies? What were you trying to accomplish
I mean,
there?
that one is iron sulfide clusters are a hallmark, highly correlated molecular structural problem that is known to use a lot of classical supercompute time and for certain methods therein. But yes, iron and how it interacts with various different other molecules and things like that are certainly of great interest to many different areas that rely on this type of physical chemistry simulation.
Cool. Cool. Let's just get personal for half a moment. You said earlier that you've been working on quantum since 2005, maybe even before then, learning and all those other things. How long have you been working on quantum? What's your journey and path been like?
Yeah, so I grew up in a family of physics. My father is a retired physics professor, and when in my university studies, I knocked on the door of a professor that was doing quantum physics research and asked whether I could learn more and get involved. And I started way back then, just getting my hands in a laboratory working on hands-on things. And then I did my PhD at Yale University, where I actually worked on some of the very first superconducting qubit experiments. This was in Professor Rob Shokoff's group. That's also where I first intersected with Jay Gambetta, who is the VP of quantum here at IBM, right?
Mm-hmm.
And actually, then I joined IBM in 2010 when we were just in the corner of the building here in TJ Watson, working away at small problems at the time, right?
Mm-hmm.
And then Jay joined about a half year later in 2011, and we really started to grow and build this whole effort out here to the point that I'd say that one really important shift was when we made the choice to take our technology, which is very physics laboratory based, put it on the cloud. That was in mid 2016.
Yeah.
And it opened up like a way of thinking about how do you program these things for a computational perspective, right?
Absolutely.
You need to make this a tool versus just a physics experiment. And that turned into, over time, Qiskit, which is our open source software development kit, right? And APIs for developers and programmers, physicists, end users. And it's continued to scale to the point that we are today.
That cloud revolution was actually pretty critical as well, because like who can afford to bring in a quantum computer into their own space, right? Like you're talking tens of millions or at least single digit millions, and you may not have the appropriate facilities for it, right? Depending on what it exactly requires, whether that's temperature, whether that's stability, whatever that might be. So that's huge, and anybody can access it, learn how to use it. As you start to work down your roadmap and as you start to bring out Starling and Blue Jay and other things like that, what's that going to mean for you? You basically been working on quantum computing your whole life. You've studied it and you're not working it. What will that mean to you?
It means it very much is my world in my life today. Aside, of course, my family and everyone at home. But it's very rewarding to see where we've gotten with this. Right from, like I mentioned, a group of us just buried in the corner of the building to really building this to the point that it's a usable technology, and I think making an impact on computation in general. I see that as, I hope this is very rewarding to me, and hopefully have true lasting impact that helps our world become a better place. All that type of stuff that's a little cheesy.
Exactly.
But I think,
Well, very few people get to participate in an actual revolution in computing or in technology in general. So it is a pretty cool place to be. Thank you so much for this time. I really appreciate it. Thank you for sharing what you know.
Thank you very much for the opportunity.